The XOR operation can take two inputs. The expression of AND is X equals A into B. So the exclusive NOR gate is the complement of the exclusive OR. X equals A into B plus A dash into B dash. Hello students, welcome to the next session of Digital Electronics. I am Dr. Soumyashri from Department of Computer Science, Vidhyaashram, first grade college. Let's start with session with some more logic gates that have been not covered in the last session. The first logic gate that we are going to get you is the exclusive OR gate. As we know, exclusive OR gate includes the OR with a slight change in the operation. The exclusive OR gate has a graphical symbol. You know about the symbol of the AND, OR and NOT, isn't it? This is the AND gate. This is the OR gate. And this is the NOT gate, isn't it? These are called as the graphical symbol. It is not actually the gate. It is just the graphical symbol of the logic gates, isn't it? So the exclusive OR has the graphic symbol similar to that of the OR gate, except for the additional curved line. Along with OR, you'll have additional curved line which will add an extension to the OR. Okay? It can take two inputs. The XOR operation can take two inputs. And the thing is, we can't construct XOR gate using 3-input XOR gate. You cannot use 3-input XOR gate. The XOR gate will always be only 2 inputs. Okay? How do you take multiple inputs? Let's check later. You have to have the XOR gate with only 2 inputs. The logical symbol of the XOR gate is something like this. Another curve added to the OR operation or OR symbol with 2 inputs A and B or X and Y, one and the same, or X1 if you take XX1 or UVWX, any value variable you can take. I'm taking 2 inputs A and B and giving the output Y. How does you check for the inputs and the outputs is the truth table of the OR, exclusive OR, or simply called as XOR, is given here. Since it has 2 inputs, how much combination you get? 2 to the power of 2, 4 combinations, isn't it? We have the input A and B with the combinations 0, 0, 0, 1, 1, 0 and 1, 1. Now, the expression of the XOR gate is X equals A into B dash plus A dash into B. Okay? The expression of AND is X equals A into B, isn't it? OR gate is A plus B. And NOT gate is A dash, isn't it? So this is the expression that we use for logic gates. Now, X has, in the XOR, expression that we use is X equals A into B dash plus A dash into B. Now, if you have this value, you can get 0 into B dash is 1. First combination, if you take 0, 0, we have A as 0, B dash complement of 0, isn't it? So, we have B represented as 1 plus A dash 0 is complemented as 1 and B is kept as it is 1 into 0, 0 into 1. If you apply the AND operation on this, both will be zeros, isn't it? So the answer output of the XOR with both the inputs 0 will give you the output 0. Alright. If you check for another combination, say 0, 1, if you take A is 0, B dash, B is 1. So complement of B is B dash. 1 becomes 0. 0 into 0 plus A dash. A is 0. Complement of 0 is 1. That is A dash. A dash will be 1. B will remain as it is. 0 into 0 plus 1 into 1 gives you 1, isn't it? 0 into 0 is 0, whereas 1 into 1 is 1. 0 plus 1 is 1. So the output with one of the input as 1 will give you the result 1. Alright. If you check for another example, say 1, 0. Now A is 1, B dash. So 0 becomes 1. Complement of B is B dash. 0 becomes 1. Now A dash. 1 becomes 0 and B is kept as it is. 1 into 1 plus 0 into 0 again will give you the output 1. Alright. And the last combination, if you check, last combination is when both the inputs are 1. When you give A is 1, B dash is complement of 1, we get is 0. Plus A dash is complement of 1, that is 0, into B is kept as it is. 1 into 0 is 0 and 0 into 1 is 0. Again, the output will become 0, is it not? So, what does the meaning of this truth table is? When both the inputs are 0 or both the inputs are same, that means both zeros or both ones. When both the inputs are same, you will get the output as 0. When you have varying inputs, you will get the 1. That means switch will be in high state when you have varying inputs for the XOR. And you will get 0 as the result or 0 as the output when both the inputs are same. Okay, this is about the XOR operation or exclusive OR operation. How do you logically express this is like X equals A into B dash plus A dash into B. This is the logical expression of the XOR operation. And symbolically you can use like this, XA, XOR. If you use circle with a plus within the circle, with the variables A and B, it represents the XOR operation. Okay. The next thing is the exclusive NOR gate. What does the exclusive NOR gate will do is the complement of the exclusive OR. Like we have NAND, complement of AND, and NOR, complement of OR. We have XNOR or exclusive NOR, which is the complement of the exclusive OR gate or XOR gate. In short, we call it as XOR gate. So the exclusive NOR gate is the complement of the exclusive OR, as indicated by small circle. How do you indicate the XNOR? Is small circle on the output side. We use a small circle, and again the XNOR gate takes 2 inputs. Alright, here we have the 2 inputs XNOR gate. Again, the condition of XNOR is that we can't construct XNOR gate using 3 input XOR gate. Only 2 input XOR gate can be used to have more inputs. If both inputs are low, since it is NOR or exclusive NOR, that means there is XNOR. If both inputs are low or both are high, then it produces the output high. Reverse of the XOR. We have XNOR. What does the XOR says is, when both the inputs are same, the output will be 0 or output will be low. When you have varying input, the output will be high, isn't it? But here it is reversal, complement of the XOR. If both inputs are low, both are high, in case of both the inputs are same, it produces the high output or 1. Otherwise, it produces the low output. That means low value. That is, when you have varying input, you will produce, or the XNOR gate will produce the low value. This is the logical symbol and the truth table of the XNOR, where you can use the XOR symbol with a circle. It represents the XNOR gate, AB and Y as the output. Now we have the combination 0, 0, which produces 1. That is reverse of the XOR. If it is 0, XNOR will become 1. If there it was 1, XNOR will produce 0. Exactly the complement of the XOR. Alright. Here we have both zeros, which produces 1. And when we have varying inputs to the XNOR gate, it produces low output. Then we have the ones. When you have same input, you will get high value. The conclusion here is, when you have same input to the XNOR, it produces the high output. When you have varying input in the XNOR gate, what you get is the low output. So this is about the XNOR gate. The logical expression you can get here is X equals A into B plus A dash into B dash. Okay. Then the symbol is X equals A circle with a dot and B. We have this logical expression, logical symbol, truth table and logical expression. Okay. Then we'll check with the 3 input and the various gates. To determine the total number of possible combination of binary inputs, how many possible combination of binary inputs to a gate can be determined by the following statement. N equals 2 to the power of n. How many inputs you can get is, the possible binary inputs you can get is 2 to the power of n possible inputs you can get, where n is the number of possible input. N is number of possible input you can get over a gate. And small n, capital N is number of possible input, and small n is the number of input variables. For example, if you have 2 input variables A and B, you will get 2 to the power of 2, 4 combinations you can get. Okay. When you have 3 input variables, then you will get 2 to the power of 3, 8 combinations. If you have 4 input variables, then you can have 2 to the power of 4, 16 different combinations. Alright. So you have all these combinations that can be used to get or to calculate how many possible inputs you can get from a particular gate. Let's check with the examples. Now we have a 3 input AND gate. Here we have 3 input AND gates and symbol with 3 inputs but produces 1 output. Okay. The combination is, we have X, Y and Z. X, Y and Z will have, that means 2 to the power of 3, 8 different combinations you can get. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 100, 101, 110, 111. Example, so you can take all zeros as the input or 0, 0, 1 as the input or 0, 1, 0 as the input. What is the result? Now you can keep like this. 0 into 0 into 0 will produce only 0, isn't it? 0 into 0 into 1 again produces zeros. The output will be 1 when all the three inputs become 1, is it not? When all the inputs is high, then only output become high, otherwise it will be low only. The meaning is that you will have 3 input switches in a gate. If you have a gate, if you consider each input as a switch, you have a house. In house you have a light. Okay? For light, for switching on the light, you have 3 switches. Okay? The light glows only when all the switches gets to the on position. Then only the light is switched on. Otherwise, if one of the input is low, if you forget to switch on one of the switch, then you will not get the bulb glowing. So this is the simple technique you can follow. When you switch on 0, 0, 0 is all switches are in off state. Obviously, light will not glow. Other than that, you have 0, 0, 1. That means I'll keep these two off and switch the first one on or switch the last one on. Last switch is changed to on state. Even then, light will not glow, isn't it? If you take 2 switches on and kept one switch off, then also it will not glow. With any on and offs, you won't get the bulb glowing. Only when you switch on all the 3 buttons or all the 3 switches, then only the light will glow, isn't it? So we have the bulb. So this bulb will glow only when all the 3 switches are switched on, right? So this is the basic thing you need to remember with the AND gate. Now we have a 3 input AND gate here. Instead of 1 AND gate, you can use 2 AND gates. 1 AND gate getting 2 inputs. This output is acting as 1 input and another input is coming which can act as an output. This is the final output. Like this, another combination is you can have like this 2 inputs, complement, you can get the output, the combination. So this is all zeros and all ones. Now this is 0, 0, 0. The output is 0. Now we have 0, 1, 0. Again, the output is 0. Then we have 0, 1, 0, 0. Then 1, 1, 0. 0, 0, 1. 0, 1, 0. 0, 1, 1. 1, 0, 0. So in red represents the 0. All zeros. 0, 0, 0. Then we have 0, 0, 1. Next is 0, 1, 0. 0, 1, 1. Then we have 1, 0, 0. Next is 1, 0, 1. Then 1, 1, 0. The last is 1, 1, 1. Okay. Only this will produce the 1. The next thing is showing this in a single statement. Say 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So, different combinations of 3 input. Here, like this also you can represent, or you can use this representation. Now, we have 3 input OR gate with 3 inputs and an OR symbol. Here we have the input table with different combinations. In this, you will get 1 if either of the input in any of these 3 inputs, if one of this becomes 1, your bulb will glow. The bulb you have fixed in the socket will glow if you switch or if you on only one switch in all of these. Or if this, or if this, or if this. If one of these inputs becomes 1, the bulb will glow. Okay. The combination representation of 3 input OR gate is like this. Here we have the same thing representing the 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0. Then we have the 0, 1, 1, 0, 1, 0. This is 1, 0, 1. Now we have 0, 1, 0, 0, 0, 1 and 0, 0, 0. 1, 1, 1. Then we have 1, 1, 0. Then 1, 0, 1. 1, 0, 0. 0, 1, 1. Then we have 0, 1, 0. 0, 0, 1 and all zeros. So, you can use like this. This 3 input representation with 2 gates can be reduced to 1 gate with 3 inputs. You can use 2 gates with 2 inputs or 1 gate with 3 inputs. Both the things are possible. Both the types of gates are possible. Alright. Now we have the same thing like 1, 1, 1. We have then 1, 1, 0. 1, 0, 0. Then we have 1, 0, 1. Then we have 0, 1, 1. 0, 1, 0. 0, 0, 1. 0, 0 and 0. So, we have the values in this gate. Alright. Then we have the 3 input NAND gate. How do you represent the 3 input NAND gate? Is AND gate with a circle and 3 inputs. The table for the NAND gate is similar to that of OR gate. You can observe here reverse of AND. Whatever there is in AND, exactly the reverse will happen in NAND gate. Okay. NAND gate is, truth table of NAND gate is similar to that of OR gate, isn't it? If one of the input becomes 1, the result will become 1, isn't it? You can use the NAND gate as with the OR and the AND gate. Okay. Next thing is to know about the 3 input NOR gate. Now we have the 3 input NOR gate like this. So NOR with 3 input. The truth table that we can view here is producing 1 only when all the inputs are zeros. When all the inputs are low, then only it produces a high output. Alright. So this is the representation. A NOR gate with 3 inputs. Okay. How do you represent the NOR gate is like this. 3 input NOR gate with same zeros and same combination. You can use 2 gates, 2 NOR gate with 2 inputs and 1 NOR gate with 3 inputs. Both can be carried out. If you check the summary, how many gates you can have is an AND gate, and, or, not, NAND, NOR, XOR, and X NOR we use, isn't it? So AND can be represented like this, X equals A into B, or can be represented like this, X equals A plus B. NOT gate can be represented like this, A dash. NAND can be represented like this, A into B whole dash. It will become A plus B. Then we have NOR, that is A plus B complement, which becomes A into B. Then we have XOR, which can be represented as A into B dash plus A dash into B, or A XOR B. Now last is the XNOR. You can represent like this, AB plus A dash into B dash, or A circle and dot within A XNOR B. So the symbolic representation of this will be like this, or can be represented like this. NOT we can represent in this way. Then NAND is OR and with a circle. NOR will be OR with a circle. And XOR will be like this. And XNOR will be like this. So this is how you can summarize the logic gates you can use in the next unit, that is about the circuits and other concepts. Thank you.